Okay, so now we want to look at 12.1b, which looks at the situation where you don't know the population standard deviations. So in 12.1a, you always knew what the population standard deviations were for both populations. That was given in the problem. But now, we're assuming that we don't know those population standard deviations. This is more like real life, okay? You're trying to investigate something about the population means because you're not sure about what they are. You only know what the sample means are from each sample that was taken from each population. So if you don't know the sample means, you're not going to know what the spread of the data is. You're not going to know what that population standard deviation is. So this is much more like real life. So what we want to do is see how we conduct a hypothesis test where we're comparing the two means again. So we're still dealing with a case where your null hypothesis is mu1 minus mu2 is equal to 0. So we're assuming that mu1 is equal to mu2. Those population means are equal. And then we've got our alternative hypothesis, which can be one of three things. It can either be does not equal, less than, or greater than 0. Okay? But now, when we get given all of this information, they're not going to tell us those standard deviations of each population. Instead, they're going to give us the standard deviations of the samples that were pulled from each population. Now, because we don't know what the population standard deviations are, when you conduct a hypothesis test, in some way you still need to have an idea about what the spread of each of the population data are. Okay, so you need to roughly know how the data in each population is spread out. Okay, because you may have one that is like really spread out and one that is all kind of bunched together. Okay, and that's going to change what happens with your population means. So there is two ways of doing this. The first way is where you don't know what the population means are, but you are assuming that they are equal. Okay, so in the first case, if you don't know what sigma 1 and sigma 2 are, you could assume that they were equal. Okay. This is the first case, so this is case 1. You can assume that they are equal to one another. So you know nothing about their actual value at the moment, but you can assume that they are equal to one another. What that does for you is it assumes that the data in each of the populations is spread out in exactly the same way in both of the populations. Okay, so they have an equal spread of data. What they actually do when they do this is they take the sample standard deviations, they square them to find the sample variances, and they average those sample variances out to find this population variance, kind of like an average, this average population variance that they're going to use for both of them. So when you assume that they are equal, the way that they do this is by finding the sample variances so you know that you are given the sample standard deviation for each one of the two samples. You have their sample standard deviation. So if you square each one of those, you're going to get the sample variance for each sample. And what you're then going to do is average them. Okay, so you're taking the average of the two sample variances. That will give you this population variance that is going to be used for both of sigma 1 and sigma 2. So what they're doing here, that's basically sigma 1 squared and sigma 2 squared, okay? So they're taking this population variance, okay, which is the average of the two sample variances, and they're going to use that population variance for both of the populations. Then all they do is you can square root both of those and you'll get sigma 1 and sigma 2, both of those population standard deviations. Okay, so what you are assuming when you do this is you're just averaging out the sample variances, okay, to give you this population variance that is then used and square rooted to find this population standard deviation that is used for both of them, and it's just an average of what we have from our sample. When you do this, what you are actually doing is pooling. That's what it's called. You're pooling the sample variances. Okay. When we actually conduct a hypothesis test in this manner, okay, you don't know what the population standard deviations are, okay? Bringing it back to what we did in chapter 11, okay, if you did not know what the population standard deviation was and you were conducting a hypothesis test, you only knew the sample standard deviation. So you had to go ahead and use a t-test, okay? If you did not know the population standard deviation, you used a t-test. And that is exactly what we do here, okay? In either one of these two cases I'm going to show you, you're going to use a two-sample t-test, okay? So in 12.1a, you had two populations. You took a sample from each one, but you were given the population standard deviations, and you were comparing the population means, okay? So we knew that we had two samples, and we were dealing with a z-test because we knew the population standard deviations. Here, we've got two samples from the two populations, but this time we don't know the population standard deviations. So we are using a two-sample t-test, okay, in either one of the two cases I'm going to show you. When you pull up a two-sample t-test on your calculator, it's found in exactly the same way. You go to stat, tests, and then go down, and option 4 on my calculator is a two-sample t-test, okay? You're inputting statistics, and it will ask you for all the same stuff that you did with the two-sample z-test. It's just that now they are going to ask you for the sample standard deviations, SX1 and SX2, as opposed to the population standard deviations that we had before, okay? So they're just going to give you that sample data this time. And at the bottom, you'll notice it will ask if something is pooled, okay? If in the problem, and they will state it in the problem, if they state that they want you to assume that the population standard deviations are equal, you're pooling those sample variances in order to find that, okay? So if they say that you're going to assume that sigma 1 and sigma 2 are equal, so if you are assuming that they are equal, sigma 1 and sigma 2, then you are pooling. So the answer to that is yes. The other case is case 2, where you're assuming that sigma 1 and sigma 2 are not equal. Okay, you're assuming that they're not equal. So if sigma 1 and sigma 2 are not equal, the question is, how do we find like a value for them or whatever? Well, the only way that you can do that is by using the sample standard deviations to estimate each one, okay? So if you don't know what sigma 1 and sigma 2 are, and you are not assuming that they are equal, you're just going to estimate each one using the sample standard deviations, okay? And then when you run a two-sample t-test in this case, you would say the sample variances are not pooled. Okay, because all you're doing to find the standard deviation of each one is just finding the sample standard deviation that's given in the problem and using that as an estimate for each of the population standard deviations. You're not taking an average of the variances and then square rooting that to find the population standard deviation, okay? So in this case, when they are not equal, okay? You are not pooling those sample variances or the sample standard deviations, so therefore you're saying they're not pooled, they're not equal, so you are just going to estimate each one from the sample data, from those sample standard deviations. Okay. When you do these type of problems, okay, in both cases, the test statistic is very much the same. There's one slight difference, okay? In this case that you have here, so for case 1, okay, again, the calculator will find this test statistic for you. You do not have to do this by hand. For case 1, your test statistic, it looks very similar to what we did in 12.1a. It's going to look like this. Okay. What this is, okay, it's very much the same as what we had in 12.1a, as I said. You've got the difference in the sample means minus the difference in the population means, okay, which this is actually just going to be 0 when you plug it in, because you're assuming, if you remember, that value is always taken from your null hypothesis, so you're actually assuming that that's 0, okay? And then you're dividing that by the square root of this thing, and that is just the standard deviation of the difference in the sample means, okay? Now, you've got this SP squared value in here. If you remember from 12.1a, you had sigma 1 squared and sigma 2 squared in there. What that would be the variance for population 1 and population 2. So if you go back and look at what that formula was for the test statistic, okay, all it was the variance for each one of the populations. But here, we're assuming that those variances for case 1, we're assuming that those variances are equal. You're assuming sigma 1 squared is equal to sigma 2 squared. And the way that we did that was by finding the sample standard deviations, squaring them to find the sample variances, and taking their average. And that was the new population variance. That is what this SP squared value is, okay? It's the average of the two sample variances, and they've used that as the estimate for each one, okay? So that's all that SP squared value is. It's just the average of the two sample variances, okay? As I said, your calculator is going to do all of this for you, so don't panic when you see this. It's just what this test statistic would look like. For case 2, this is going to look very much the same. The only difference is this value here is going to become the variance for the first sample, and this value here is going to become the variance for the second sample. Okay, remember the variance is just the standard deviation squared, okay? And we're going to estimate each one of those population variances and each one of the population standard deviations by what the sample data gave us. So a population standard deviation is estimated by the sample standard deviation. Therefore, the population variance is going to be estimated by the sample variance. So each one of those, and now we're not assuming that they're equal, we are just taking them from the sample data, like we said up here. So if you go ahead and look back at what we did in 12.1a, we're just assuming that each one of those sigma 1 squared and sigma 2 squared values is now equal to S1 squared and S2 squared, those sample variances instead. That is the only difference. So I'm going to go ahead and do an example of this in a second, but what I want to look at quickly is exactly the same as what we did last time again, okay? If you have a two-sided alternative hypothesis, okay? So if you have a hypothesis for your alternative hypothesis that has that does not equals in it, you can also conduct a hypothesis test for that using a confidence interval. But in this case, we're going to have to deal with a two-sample t interval, okay? If you remember in the last 12.1a, we dealt with a two-sample z interval. In this case, because you don't know what those population standard deviations are, you've only got the sample data, it's going to be a two-sample t interval, which in my calculator, if you scroll all the way down, it's option 0, okay? This only works if you are dealing with a two-sided alternative, okay? If you look at my notes, I actually have what the t-interval looks like. It's a very horrible formula. But again, all that t-interval is looking at is it's looking at the difference in the sample means plus or minus some value. Okay? I will actually write it out just so that you have it. This is what the confidence interval looks like. Just make sure. Should be -2, and then square root. I'm going to do this for assuming that we have pulled those sample variances. So let's say that this is your interval. Okay, this is your confidence interval. Okay, you've got the difference in the sample means plus or minus some t value. Okay, this is all one value. It's just some t value times that standard deviation of the difference in the sample means. Okay, again, don't worry too much about this formula, but this is what your calculator is looking at. Okay, it's very much the same as what we did in 12.1a. It's just that now we're looking at this t interval as opposed to a z interval. When you do this, okay, what you are looking at is how close together x1 bar and x2 bar are. Okay, when you do this, as we did in 12.1a, you are looking at whether 0 lies in this interval. Okay? Because you've got the difference in the sample means plus or minus this small value. Okay? This whole thing's going to end up being a pretty small value in most cases. So if 0 lands in there, what it means is the sample means x1 bar and x2 bar, so the means of each of the samples, are close enough together that we can therefore assume that the population means are equal. Okay, so if 0 lies in that interval, it means that x1 bar, the sample mean, actually I should write it as x1, and x2 are close enough together that we can assume that mu1 is equal to mu2, which means that mu1 minus mu2 is equal to 0, which means we fail to reject the null hypothesis. Okay, so if you calculate this 2-sample t interval, okay, if you do not know what those population standard deviations are, you only know the sample standard deviations, you go ahead and do a 2-sample t interval. Okay, you go ahead and do that. As I said, on my calculator it's option 0. Again, they will ask you for whether you are pooling those variances. Okay, so you're going to type in your sample standard deviations, but what it wants to know is what to use for these two values up here. Okay, it's either going to use the sample standard deviations to estimate what those ones are going to be, or it's going to use this pooling technique where it takes an average. Okay, so you have to tell it whether to pool it or not, and it will tell you that in the problem, so please read the problem carefully. Okay, but if you go ahead and figure out what this interval is, it's on a 2-sample t interval. Again, only works for a 2-sided alternative. Okay, for a 2-sample t interval, if 0 is in there, you're going to fail to reject the null hypothesis. You could assume that those population means are equal. If 0 is outside of that interval, it means that the sample means are just too far apart, that therefore you cannot assume that the populations from which they come from have the same mean. So in that case, you're going to reject the null hypothesis if it falls outside. Okay, so that's 2 ways of conducting this hypothesis, depending on whether you want those population means to, the population standard deviations to be equal or not. Okay, but it will tell you that in the problem. But it's all conducted either by just doing a 2-sample t-test or by doing a 2-sample t interval. If you have a 2-sided alternative, you can do that 2-sample t interval. It's up to you. just as a heads up, when you do this, either you pull the variances or you don't, and that determines what your samples, what your population standard deviations are going to be, and therefore what your population variances are going to be. When you do that, if you do not pull them, so you assume that they're different and you're just assuming that one population standard deviation is equal to that sample standard deviation, and same with the other population standard deviation, it's going to equal the sample standard deviation for that other sample. If you do assume that that is the case, you are actually taking a more conservative approach, okay? In terms of intervals, you would actually end up with a wider interval if you don't pull the variances as opposed to when you do, okay? But it would always tell you in the problem as to whether you need to pull them or not, but you would always end up with a wider interval if you don't pull them than when you do. Okay, if you go ahead and look at my notes on the Google Drive, right at the end of page 6, I have an example, and we're going to go through that quickly, and it's very similar to what you find in the homeworks, okay? It's the end of page 6 on my notes for 12.1. And it says that a researcher wants to see if there is a difference in the mean heights of college men and women, okay? So we know that we're just looking at a difference here. A random sample of 13 men had a mean height of 70.1 inches and standard deviation of 2.19 inches. A sample of 10 women had a mean height of 64.3 inches and a standard deviation of 2.21 inches. Assume that the population variances are equal, so we know that we're going to be pooling those variances, and that the populations are normally distributed. Determine an 80% confidence interval for the difference in the population mean for height of men and height of women. Okay, so the first thing we want to do is they're actually asking you for a confidence interval. We'll conduct a test in a minute, but let's go ahead and do one of these intervals. So you know that at the moment you want to see if there is a difference. We'll write down what our null and alternative are going to be. So our null hypothesis is assuming that mu1 is equal to mu2. Okay, it's always the same thing, so that means mu1 minus mu2 is 0. And your alternative is assuming that the two population means are different. So one minus the other is just not equal to 0. Then you have 13 men, so the first sample has 13 people in it, with a mean, so x1 bar, okay, the first sample mean is going to be 70.1. And the standard deviation of that sample, so S1, is going to be 2.19. Then you've taken a sample of 10 women, so N2, the size of the second sample is 10. The mean of that sample was 64.3 inches, and its standard deviation was 2.21. Okay? Now you're assuming that the population variances are equal, so you are pooling, okay? Because it says that you are assuming that the population variances are equal, that means you're assuming the population standard deviations are equal. So we know that we've got to pool those sample variances, those sample standard deviations, in order to find this average that will give us this population standard deviation, that population variance, okay? We want an 80% confidence interval. Okay, so let's go ahead and do this on a calculator. So at the moment we're looking for an 80% confidence interval. So I want a 2-sample t interval. So x1 bar is 70.1. Sx1 is that first sample standard deviation is 2.19. N1 is 13. X2 bar is 64.3. Sx2 is that second sample standard deviation, which is 2.21. And then N2 is 10. Our confidence level would be 0.8 with that 80% confidence. And we are pooling those variances because we're assuming that they're equal. And we can go ahead and calculate. Now the interval that I got was 4.5763 and 7.0237. Okay. If we were going ahead to conduct a test on this, 0 is not in the interval. Okay, if 0 is not in that interval, it must mean that our sample means are far enough apart that we can't assume that our population means are equal. So 0 is not in the interval. We're going to reject the null hypothesis. We're going to reject H0 in favour of the alternative hypothesis. So what does that tell us in terms of the problem? That tells us that the mean height of men and women is different. Okay? So we know that mu1 does not equal mu2. If we were to go ahead and do this the other way, okay, we've got a two-sided alternative hypothesis here. So we could have done it using this confidence interval, or we could have done it using the two-sample t-test. So let's go back to stat and tests and conduct a two-sample t-test, okay? Put in that exact same data. On my calculator, it comes up automatically because it knows I've just done it, okay? And if we go ahead and conduct this and calculate, okay, and you put in the exact same numbers and you're going to pull those variances again, okay? In this case, okay, it's going to come up with T. That is your test statistic, okay? So if you were to go ahead and do test statistics compared to critical values and go that route, okay, then you could use that T value, that's 6.272 roughly, okay? Then it comes out with this P value, okay? So I have P is 3.20825 times 10 to the negative 6, okay? That P value, okay, let's write out roughly what it is. It would be 3.21 by 10 to the negative 6, okay? That's a really, really small P value. We don't have a significance level alpha. However, we have been given a confidence level, okay? If we are 80% confident, okay, that means that 80% of the time we want to fail to reject the null hypothesis, okay? Which means that 20% of the time we want to reject our null hypothesis, which would give us a significance level of 0.2, okay? So because we've got an 80% confidence interval, okay, that means that alpha, okay, the amount of time that we actually don't want to be confident and we want to reject that null hypothesis is going to be 20% of the time, which means alpha is 0.2. So you could go ahead and do that and compare P to alpha. Well, P is most definitely less than alpha, so we reject the null hypothesis. So either way that you do this, you're going to end up with the same answer, whether you want to, in this case, because you've got a two-sided alternative, okay, we know that we can either do a two-sample t-test and compare P and alpha, or we can do a two-sample confidence interval, a two-sample t interval, and we can go ahead and find this confidence interval and see if 0 is contained in it. So either way that you want to do this is fine, as long as you have that two-sided alternative. If you only have a one-sided alternative hypothesis, so you have a less than or greater than, you have to go ahead and use that two-sample t-test. You can't do a t-interval. A t-interval test only works if you are using a two-sided alternative. Okay, so keep that in mind. That is the end of this chapter. It's not a very difficult chapter once you get the hang of it, because it's all done on a calculator, but please make sure you read the question with this one, because I've had a lot of issues with people in the past that don't read the problem and then forget when they need to pull the variances and when they don't. So make sure you read the question in this one. Number one, to make sure that you get your samples the correct way around, especially when you're dealing with a less than or greater than. You have to make sure that you get them the right way around in the calculator, because otherwise you may be proving that one is less than the other when in fact you need it to be proved that one's greater than the other, and you've just got stuff the wrong way around, okay? So make sure that your sample data is the right way around, and secondly, make sure that you know when you're pooling stuff, okay? That is the main thing with these. And then also make sure that you know when you're conducting a z-test and a t-test, okay? We're going to be doing a ton of these, so you need to be able to look at a problem and know when to use what test. So get into the habit of that now, early on, because we've still got a couple more chapters of this kind of stuff where you're going to have to then use a different test again, and you're going to have to be able to identify when to use what test, okay? So remember right now that if you are given the population standard deviations, hence the population variances by squaring them, then you know that you can use a z-test. In this case, we're dealing with two different populations, so it's going to be a two-sample z-test. If you are not given those population standard deviations, and hence you're not given the population variances, but you are given those sample standard deviations, then you know that you can use a t-test. Again, we are dealing with two samples and two populations, so it's going to be a two-sample t-test. If you have two-sided alternative hypotheses, then you know that you can also conduct these tests using confidence intervals. Make sure you get the right one again, whether it's Z or T, but you can use those confidence intervals instead and look at whether zero lies in them, okay? That is the end of this video. Go ahead and try the homeworks. If you do have any issues, please let me know, because I know that this stuff can be confusing, but I'm more than happy to help you and talk you through it again. And I will see you in the next video.